Hey guys, and welcome back to my channel. It's been a while, and this video is going to be a chemistry topic. In fact, it's going to be stereoisomers, and this is structure 3.2.7 for IB students. But if you're not an IB student, you can also, of course, watch if you're just curious or if you're learning for another curriculum, because most of the time these things overlap. So what are stereoisomers? So in comparison to structural isomers that have different structural formulas, stereoisomers have the same structural formula but different 3D spatial arrangements. And we'll see what I mean by that in just a second with concrete examples too. And there's two types of stereoisomers. There's cis-trans stereoisomers and there's optical isomers, or at least these are the two types that we study here. And let's take a look at each and every one of those. So cis-trans isomers. This type of isomer occurs when their rotation around a bond is restricted. So this happens when there's either a double bond or we have a cyclic compound, like a cycloalkane. It also happens with triple bonds, but we don't look at that for the IB syllabus, so I'm not going to mention it here. So when looking at the double bonds, we can have the substituent, which is this part that I circled in red right here, on different parts of the double bond, or on different sides of the double bond. And this substituent can be anything that is bonded to this carbon right here. So if both of the substituents are on the same side, we are going to have a cis isomer. And this is quite easy to remember because cis, same, sounds pretty logical and is also logical word-wise. But if we have substituents on opposite sides, so like here, for example, we have A and A right here, but B and B right here, so on opposite sides, then we're going to have a trans isomer. And the idea behind this is because the rotation around the bond is restricted, and what I mean is the rotation around this bond is restricted, you can never get these molecules to become the same, right? You can never get this part to turn upside down while this other part stays the same, and therefore never will these two molecules perfectly match up, and therefore there are isomers. Now let's look at an example, and we can look at but2-ene, so C4H8, and here look for yourself and identify which is the cis and which is the trans isomer. So I hope you have done this by yourself just to see what it is, and let's just take a quick look. Here we have our substituents on the same side, so we're going to have a cis isomer, and we can just write this as cis dash but2-ene, and then here we have them on opposite sides, so this is going to be trans but2-ene. And again, these molecules are different and they are never going to be exactly the same, hence them being isomers. Now let's take a look at cycloalkanes and how this results in stereoisomers. Again, in cycloalkanes, there's no rotation around the bond. So for example, over here, you cannot rotate different parts and it's always going to have the same orientation in space. So here we have a cycloalkane, which is a cyclopropane because we have 3 carbons here, and we have 2 different isomers. So on this isomer, all of the substituents are having the same orientation in the sense that they're all bending either out of or into the plane, right? If we were to look at this is our flat triangle, and they're both either coming out or they're both going in. And so this is going to be our cis isomer. Now in this other example right here, they're going out into different planes. So this one, for example, is going front and this is back, or the other way around. And what this looks like is like this. And so these will never be on the same plane. And so these two molecules will never be perfectly the same because for one of them, if you look, both are going in or out, but for the other one is going in and one is going out. So if our substituents are on different planes, then we have a trans isomer. And let's take a look at an example, which is going to be 1,3-dichlorocyclobutane, and we have cyclobutane, so 4 carbons in a cycle, and 2 chlorines on 1 and on 3. And look for yourself and determine which is the cis and which is the trans isomer. So here we have a chlorine that are both going out onto the same plane. So this is going to be our cis isomer. Again, cis, same. And here they're going into opposite planes. So this one is going, for example, back. This one is going front. And here we're going to have a trans isomer. Now let's move on to optical isomers. Optical isomers occur when we have a chiral carbon. And a chiral carbon is a carbon that is bonded to 4 different groups. And what makes it special is because if a carbon is bonded to 4 different groups, it's asymmetrical, so it's unbalanced due to the dipoles, and it has different geometries on each of those 4 different groups. So for example, one is longer, one is shorter, etc. So this is what it looks like here. So we have, for example, group A going up, group B going back, group C going front, and group G on the same plane as A. Now, the isomers arise if we take mirror images of, for example, this one molecule that has a chiral carbon. Because once they're mirrored, these two are non-superimposable. And that means if I take this molecule, let me copy it, and I try to match this up, it will never work. For example, right now I have C and A are matched, but D and B aren't. If I try to, for example, match B and D, so they're like this, then A and C won't match, etc. So there's always going to be 2 different substituents that don't match in their position if you have these 2 mirror images of each other. And these optical isomers, which are also called enantiomers, by the way, they're optically active. And what I mean is that whilst, again, they have the same structural formula, they have different molecular orientations in 3D space. And they have the same physical and chemical properties, except for the way or the angle at which they rotate light. So these enantiomers rotate polarized light in opposite directions. More specifically, they rotate it in opposite directions at the same angle, but you don't really have to know that. So as a result, they interact with other chiral substances and are optically active molecules. So let's take a look at an example of an optical isomer or of an enantiomer. So the example is butan-2-ol. And a tip that I give you for optical isomers is that sometimes they're not so obvious. You always have to not consider for example, atoms that are right next to a carbon. For example, here will be the H and the O and the H and the C, but rather consider the fact that your substituents can be large groups. So for example, what I mean is that here you have one substituent that is CH3, the other substituent is OH, the other substituent is the H, and that's another tip, never forget the H that's bonded to the C. And then our last substituent is this whole chain right here. So this right here is our chiral carbon. And once again, notice all of our substituents are different. This is CH3, this is OH, this is H, this is CH2, CH3, right? So now I challenge you to draw this in its 3D structure and draw the 2 enantiomers. So I hope you have done that, because this is, and of course there's different ways that you could place these oppositely and whatnot, but this is just how I have drawn it. And if you have your chiral carbon, you have your H, you have your CH3, you have your OH, and you have your CH2, CH3 right here. And you take a mirror image, and you end up with 2 enantiomers. And again, these 2 are completely different in their 3D orientation, and you will not be able to get them to have the same orientation ever. And lastly, what I wanted to mention, and this is something that I think might be specific for the IB curriculum, is the racemic mixture or the racemic mixture. And this is a mixture that is a 50-50 ratio of these 2 enantiomers, and its specialty is that it appears to be optically inactive, because half of the light is rotated at one angle and the other half is rotated at another angle, so in the end both cancel out. but in reality it consists of enantiomers and it is optically active technically. So I hope you enjoyed this video. I hope you learned more about stereoisomers. Don't forget the two types. I would say that it's all pretty simple. You just have to be attentive when looking at molecules and recognizing all these different substituents. So remember your cis-trans isomers, remember your optical isomers, and have fun. Bye bye!